In this lecture, we'll look at estimates of VO2 max as a way to evaluate cardiorespiratory fitness, and we'll also look at graded exercise tests. VO2 max is the standard measure of cardiorespiratory fitness. It's the maximal rate of oxygen consumption. VO2 max is expressed either as liters per minute, or if you want to normalize by the person's weight, you'd have it's often expressed as milliliters per kilogram per minute. VO2 max is usually measured with a graded exercise test, or GXT. And furthermore, there's a national database of VO2 max values across age and sex, which can be used to compare individuals. This database was generated by the American Heart Association. It turns out that if you're measuring the cardiorespiratory fitness of a person, VO2 max is very reproducible, given that you're looking at an individual using the same equipment and the same protocol. VO2 max may be tested either using a continuous or a discontinuous graded exercise test. In a continuous test, which is probably the more common type, you'll start at a certain intensity of exercise, and the person will do that for about 2 to 3 minutes. Then they'll go to a next higher level of exercise and continue to go up higher and higher like that, all in one session without any interval between each stage. In a discontinuous graded exercise test, a person may do a stage and then wait a few hours and do another stage, or even come back another day and do the next stage. There are differences in VO2 max values for one individual given the type of exercise being done. So if the person does the exercise using a treadmill, that'll yield the highest VO2 max value if the person is running. If a person's walking on a treadmill and we try and do an estimate of VO2 max values, we'll typically get a value that's about 6% lower than running. Furthermore, if we go to a cycle ergometer, we'll also get a lower value than with running. So a cycle ergometer, of course, works the legs. Well, there are also arm ergometers, and those will yield values of VO2 max about 70% that of a typical bicycle or leg ergometer. In other words, about 30% lower. Now, because of all these differences in VO2 max, depending on the type of instrument that's being used, it's become a convention to sometimes use the term VO2 max to refer to a graded running test, because that yields the highest value. And the term VO2 peak is commonly used to refer to maximal values on walk, cycle, or arm ergometer protocols. VO2 utilization increases with increasing workload during a graded exercise test, as you can see in this graph. Eventually, you reach a highest VO2 value, and that's referred to as VO2 max. This value represents the maximum ability of the cardiorespiratory system to deliver oxygen to contracting muscles, and the ability of muscle to take up O2 and produce ATP aerobically. However, for about 50% of individuals, once you get to this VO2 max, they have to stop. They've essentially have reached a point of complete fatigue, and that they're not able to go any further. Now, the issue that arises is, how do we know that that's truly VO2 max? If a person's able to go to the next level and continue to exercise for a little bit, then we can then we know that this really is a truly VO2 max. The way they can do this, of course, is by doing anaerobic metabolism in order to make up for the energy deficit. But if an individual isn't able to do this, then you simply stop at this value. We wouldn't know for sure that they weren't able to go to the next level, right? So because of this problem, secondary criteria have been developed to provide evidence that, in fact, the person did get to their maximum VO2 value, or their VO2 max. As I stated in the previous slide, when a subject doesn't reach a plateau in VO2, how can we be sure that the person has in fact reached VO2 max? And for this reason, there's a number of secondary criteria that will help us to determine this. One of the simplest criteria is to simply to look to see if there's been a leveling off in VO2 values. For example, with a test in which we're using a 7 mile per hour treadmill speed, and we're increasing the grade to make the work rate higher, and we're increasing by 2.5% for each stage. In this particular test, an increase of less than 2.1 milliliters per kilogram per minute has been taken to indicate that a plateau has been reached. Another way of looking at trying to determine whether a plateau has been reached is to look at the level of blood lactate. Of course, this gives us an indication of the level of anaerobic metabolism. So if the post-exercise blood lactate level is greater than 8 millimoles per liter, this is also an indication that the person may have reached VO2 max. Yet another indicator is a high respiratory exchange ratio, or R of greater than 1.15. Now, recall that the respiratory exchange ratio, or R, is the ratio of carbon dioxide produced to oxygen consumed. So it's VCO2 divided by VO2. Respiratory exchange value of 1 indicates that carbohydrates are being oxidized. If R is above 1, then carbon dioxide is being released at a faster rate than oxygen is being consumed. And how can this occur? Well, one way that this can occur is if there's an accumulation of lactic acid in the blood, which of course it would be due to anaerobic metabolism. This leads to an acidification of the blood, and this leads to an increase in the blood CO2 level. So PCO2, or partial pressure of CO2, is increased. And when this happens, then there's a greater difference in the partial pressure of CO2 between the blood and the pulmonary capillaries and the PCO2 within the alveolar airspace. And so there's a quick offloading of CO2 due to this increased diffusion rate. And so the person will offload a lot of CO2, and that's how you can get to this R value, which is above 1. And of course, this, again, would indicate that the person is doing a high level of anaerobic metabolism. Yet another indicator that the person is reaching VO2 max is to look at heart rate. So you could look at, for example, the age predicted maximal heart rate, and you use that equation to determine what the maximal rate is for a given person. And then if the heart rate is within 10 beats per minute of that value, then we can, the feeling is then you could assume that the person is at VO2 max. The usefulness of this has been questioned, though, because one of the problems is there's so much variation between one individual and another of the same age. So that method has to be taken with a little bit of a caveat, because it doesn't really use information about that individual. And finally, we should note that not all subjects will meet all the different criteria. So, for example, you may have like 20% of women who meet the leveling off criteria, which is this 2.1 milliliters per kilogram per minute criterion. They may meet that, but they don't reach an R value that's greater than 1.0. So it's very difficult. It shouldn't be expected that you'd meet all these different criteria simultaneously. Interestingly, several studies have demonstrated that a plateau is not needed for the measurement of a true VO2 max. So typically the way this has been shown is the experimenters would use a graded exercise test. And so you would see VO2 going up and up and up, and it would not necessarily hit a plateau, but the person would be exhausted and stop. There'd be some criterion with which you would end the exercise test. What they would then do is a day or two later have the person come back, and then instead of going through all the different earlier levels, they would go right to that VO2 max value, or actually give, or straight to a higher value. In fact, the next step higher, right, where they would have gone. Like if it was a treadmill and they're doing 7 miles per hour and they're doing, say, 2.5 increase in grade each time, now they would go to the next 2.5 greater than the greatest grade that the person had done in the previous test. And what they find is that, okay, the VO2 value is actually the same. So this person wasn't able to use more oxygen, even though we're just having them start off at the very high level. So you might have expected, okay, maybe they were fatigued or something like that, and that was leading to this previous VO2 value, which with in the stopping of the test. But in fact, they aren't able to use any more oxygen. So that shows that it really is a true VO2 max, because when you have them start from a well-rested state at this high intensity level, they just simply can't use more oxygen. So that does indicate it's something intrinsic to the person. It could be their cardiorespiratory system. It could be the way that their muscles are able to extract oxygen from the blood and use oxygen. Another thing to keep in mind is as you do these tests, you're going to do things like vary the work rate, the duration of each stage, determine rest intervals, warm-ups, gas sampling intervals. So all these things have to be done in a very consistent manner in order to get consistent results. So this is why we're discussing right now all these different protocols and how they would be set up very scientifically. So you have everything in place when the person does come in to get tested. And of course, there are big variations. So for example, you do have to tailor the test for individual people. So for example, for a young healthy person, you might start off with a graded exercise test at a much higher initial work rate than you would for someone who's elderly and who's not really in good shape. As I stated earlier, the real standard is to actually measure VO2 max on a treadmill or using a cycle ergometer or some sort of lab quality equipment and so forth. But this is actually not always practical. If you're trying to assess, say, a whole classroom or something like that, and you want to do it in an efficient manner, well, it'd be too complex and time consuming to try and bring in every single person in a class and do this. And so for this reason, a number of equations have been generated, a number of protocols have been generated to help calculate an estimated VO2 max. And the way these work, they all work differently. There's different strategies and so forth. But one of the common themes is they often will use a graded exercise test, and they'll use either the last stage or the very last two stages to then do some sort of extrapolation to figure out what the VO2 max is. And we're going to talk about that in great detail in other slides, so I won't go into it right now. One of the big key points, though, is in doing these testing, though, is you must allow time for the subject to reach a steady state in each stage. And there have been various studies about this. But generally, in most of these tests, each stage will last about 2 to 3 minutes. And that seems to be sufficient time to allow the person to come to a steady state. And then you would measure various parameters. Like, for example, if you're measuring heart rate, towards the last 30 seconds or so of that 2 or 3 minute interval, you would then measure heart rate, and that would be the heart rate for that particular stage. One issue with doing an estimation of VO2 max is you're not actually measuring it very directly. And when that happens, you're always going to introduce some error. So your book talks about this term standard error, which is a measure of how precise an estimate is. So if you have a parameter that's normally distributed, which means it has a mean value and there's a sort of a bell-shaped curve around it, then one standard error describes 68% of the estimates compared to the true value. So these tests are developed to determine VO2 max in an indirect manner. And what they do is they test a large number of subjects. For example, maybe you wanted to look at school-age children and estimate their VO2 max. You would take a subset of children and actually take them into a lab and measure their VO2 max very carefully. Then you would measure how they do on, say, a mile run or various other tests. And then you would compare a number of individuals with them, and then you would start to get an idea of how the performance on a particular test correlates with VO2 max. And of course, they do controls and all sorts of things like that. But eventually what you get is an equation, and the equation allows you to plug in numbers that you got from the test, and then you can determine what VO2 max is, or an estimated value of VO2 max. So now, depending on the different tests, you'll have different standard errors. Standard error essentially gives you an idea of how far off the predicted VO2 max is from the actual values. So for each individual, there is a true VO2 max, but you may get a value that's a bit different from that true VO2 max. And it depends a little bit on how accurate the particular protocol is. So for example, VO2 max can be estimated from the last stage of a maximal test. So a maximal test is an increment, typically a graded exercise test, in which you will bring the person up all the way to like 90 to 95% of VO2 max. And then that top value is just assumed to then be VO2 max. Well, if you look at the standard error, so about 68% of the estimates will be within 3 milliliters per kilogram per minute, which is not bad. Now you could do VO2 max estimated from heart rate in a submaximal test. So in a submaximal test, again, it's typically a graded test in which you increase the intensity of the exercise in steps. But at this point, with a submaximal test, you don't go all the way to 90 to 95%. You might stop more in the range of say 70 to 85% of VO2 of the estimated VO2 max, or say of the maximal heart rate would be another way of looking at it. So this is not quite as good as using a maximal test. With a submaximal test, about 68% of the individuals will be within 4 to 5 milliliters per kilogram per minute. So it's a larger error. The standard error is higher. Finally, with a test like a 1 mile walk or a 12-minute run, then you have an even greater standard error, about 5 milliliters per kilogram per minute. So as we get further away from the sort of gold standard of doing measuring VO2 max within a lab, you can see that the error increases. Now, that sounds bad, and it is if you're trying to very scientifically measure exactly what the VO2 max is. But in a lot of instances, it doesn't really matter. Like, what you're trying to get is just an overall idea of how healthy the person is, what their cardiorespiratory function is. So it's a bit of error is actually tolerated. And one way of looking at it also is if there are often with the errors that are inherent in these sorts of measures, if you follow one individual over time, well, they'll have the same sort of error. So if a person was to do a 1 mile walk, and then they continue to exercise daily for a certain number of minutes per day, and then they came back and a month later they did that 1 mile walk again, then if they see an increased VO2 max estimate, then that's a good indicator that they're doing a good job and they're getting more fit. And so in these sorts of cases, often you don't need perfect accuracy, and yet it's still very very helpful and maybe even motivating for the person who's trying to get fit. There are various ways to estimate VO2 max. One way, of course, is the direct method, in which you're actually in a lab and you actually measure, say, oxygen uptake. And then there are other methods, such as looking at the work rate. Another common method, though, is to look at the heart rate response. And so the way this would work is typically this is done with a graded exercise test. So, for example, in this graph here, we can see that we have a certain work rate, 300 kilopond meters per minute. So recall what the unit kilopond meters is. So a kilopond is the amount of force generated by a kilogram under Earth's gravity, so under the acceleration due to Earth's gravity. So this is a force, just like a Newton is a force. So we have a kilopond force, and that's multiplied here by meters, so a kilopond meter. So this is force applied over a certain distance. So that's actually work. When you apply force to an object, say over a certain distance, you're applying work to it. This is equivalent to energy also. Now, when you divide by minutes, you're saying, well, how much work are you doing per unit time? And that's a work rate. And that's also can be used as an indication of power. So, for example, watts is joules per second. And again, that's going to be a joule can be thought of as a unit of energy or a unit of work, and it's per second, so it's per unit time. Okay, sorry about that, but that's so what we have here is work rate, so 300 kilopond meters per minute, and then we're increasing the work rate. And so this is a graded exercise test. So for example, it might be a person running at 7 miles per hour on a treadmill, and we're gradually increasing the incline level in increments of say 2.5 percent. And what you see is that the work rate increases and the heart rate increases pretty linearly. And eventually we're going to stop here. So this is going to be a submaximal test. So we're going to stop at 85% of the maximum heart rate. How do we know the maximum heart rate? Well, typically we'll just estimate that. So we'd say, well, this person has an age is 20 years old, and therefore using a formula, we'd find out that their estimated maximum heart rate is 200. Then we would multiply 0.85 times 200, and that would give us a maximum heart rate of 170 beats per minute. So basically, when this individual reaches 170 beats per minute, they can stop. And then because this is so linear, we then extrapolate from this linear curve, and we extrapolate to the point where we get to their maximum heart rate, which is 170, right? Now, hold on. Estimated heart rate is 200, so up to 200. So we go to 200. Then from that point, we say, well, this is what their heart rate would be if they're working at their maximal rate. Everything's linear, so now we can determine what the work rate would have been. In this case, it's 1,200 kilopond meters per minute, okay? And then we can then also determine, because there have been many studies done with many healthy people and so forth, and they've said, well, given this work rate, how much oxygen would a typical person be using? And then we can, so we plug this value into an equation, and here we get 2.7 liters per minute. So we're able to estimate VO2 max from the heart rate. We didn't measure, oxygen at all. We just measured the heart rate, and we didn't even have the person go all the way up to their maximum heart rate. And there may be reasons for doing this. Perhaps you have some worry that this person appears healthy, but maybe they have some sort of arrhythmia or something going on with their heart, and you really don't want to push them all the way to their maximum heart rate. And there really is no need to. You could just go up to 85%, and you can get a good estimate of VO2 max this way. With any kind of estimate, there of course are problems. One problem is that there's a large standard deviation of age-predicted maximal heart rates. So a standard deviation, again, it's a little bit different than a standard error. I'm not going to get into technical details, but it gives you an idea of what kind of range is found in the actual population of people out there for a given heart rate. So, for example, for this person, their maximal heart rate was 200. But perhaps there is a range, right? So perhaps his maximal heart rate is really 211. Or maybe it's 189, right? So if there is a certain standard deviation of, say, plus or minus 11 beats per minute. So because of this error, you'll end up finding, for example, if his heart rate, maximal heart rate is really 211, then this should be continued out further, and then you would drop down and you'd find a higher work rate. But what if his maximal heart rate was only 180. Well, then we're overestimating. So there we're underestimating his VO2 max. What if this person actually really isn't in such good shape compared to other 20-year-olds, and his maximal heart rate's only 180? Well, then you should really be dropping down from 180, right, from his maximal heart rate to find his work rate, maximal work rate. And so by just sort of using standard numbers from a whole population of people, we're getting numbers that are a bit wrong. In this case, we'd be overestimating this person's VO2 max. And then there are other factors that have to be thought about when you do any kind of test like this. You have to worry about whether the person's dehydrated. If the temperature is very high, then that can have a very negative effect on it'll lead to higher heart rate than you would have otherwise. A very humid environment, particularly combined with high temperature, can lead to making the exercise essentially much more intense and difficult than it would be otherwise. Medications can also have an effect. So again, these are problems, but despite these problems, the estimate of VO2 max still does provide useful feedback to the participant in a fitness program. And again, it can, since you're often in many cases, for example, if we're talking about a person who's a little bit less fit or a little bit more fit than other individuals in his or her cohort, in other words, people of the same age, well, that overestimate or underestimate of VO2 max would still be consistent from measuring the person from one day to a month later measuring that same person. And so it would still provide a very good feedback onto how they're progressing in terms of their fitness. Here are some take-home messages. The measurement of VO2 max is the gold standard measure of cardiorespiratory fitness. VO2 max can be estimated based on the final work rate achieved in a graded exercise test. VO2 max can also be estimated from heart rate responses to submaximal exercise by extrapolating the relationship to the subject's age-predicted estimate of maximal heart rate. Careful attention to environmental factors, such as temperature and humidity, needs to be done because these can affect heart rate response to submaximal exercise. Here are some things to keep in mind when you're doing graded exercise tests. First of all, graded exercise tests may be submaximal or they could be maximal. And so a choice needs to be made based on the population that's being tested. So for example, with healthy young people, you might be justified in doing maximal tests. For young children, that's probably not appropriate. You might want to do submaximal tests. And for older people, older individuals who are perhaps a bit sedentary and out of shape, a submaximal test would clearly be more appropriate for that population. So the starting work rate is also related to this. So for a sedentary subject, you might start at 2 to 3 METs. Recall that a metabolic equivalent, or MET, is an objective measure of the ratio of the rate at which a person expends energy relative to the mass of the person. So for example, when a person is performing 1 MET, that's equivalent to the energy expended when a person just quietly sitting, not doing anything, so perhaps reading a book. And so that, for an average adult, translates to 3.5 milliliters of oxygen per kilogram per minute. So again, for a person who's not in really good shape, you'd start at maybe 2 to 3 METs, so really quite light exercise. And then you increase in maybe 1 MET per stage, and eventually ending at some sort of preset value, depending on, say, heart rate or something like that. And one of the things to keep in mind is, of course, the duration of each stage. So each stage, again, would last about 2 to 3 minutes, which should be enough time to allow for steady state to be reached. The mode of exercise is another thing that should be kept in mind, whether you're going to use a treadmill, cycle ergometer, or step test. And we'll talk about all 3 of those in more detail. And I should mention, let's say for a person who's younger and healthier, then you might want to start at a much higher level. So again, 1 MET is equivalent of metabolic equivalent task of just sitting there and just reading a book, say. So you might start with an active, healthy young person at 5 METs. And then instead of going up at increments of 1 MET, you might jump by 2 to 3 METs per stage. And again, you'd end the exercise at some preset, say, level of heart rate or something like that, or work rate value. Particularly if it's a submaximal test. Of course, the subject must follow instructions carefully. And of course, environmental conditions should be controlled very carefully, particularly with paying particular attention to temperature and humidity. Oh, and the other thing with the stages, so if these increments or the stages between, the intensity of exercise, it does increase from one step to the next or one stage to the next. If those steps are too large for an individual, that can lead to problems with estimating VO2 max. And typically it would lead to an overestimate of VO2 max. And a very similar problem occurs if each stage is too short. Let's say you just did 45 seconds per stage. Well, at that point, the person hasn't really come to an equilibrium yet, or a steady state, I should say, steady state for each stage. And so again, you're going to get an overestimate of VO2 max for that individual. So fortunately, you don't have to work all this out on your own. Many of these protocols have been developed over many, many years and have been really well worked out. And there's a lot of scientific evidence for why they work and so forth. So one example is this one here, the National Exercise and Heart Disease Protocol for Poorly Fit Subjects. So for these poorly fit subjects, you might start at, say, stage 1 with a MET of 2.5. So it's quite light exercise. That corresponds to a speed of 2 miles per hour on a treadmill and a grade of 0. So that's very easy. And then you would increase every 3 minutes. Each stage is 3 minutes. Every 3 minutes, you'd increase by a stage. Next stage is 3.5. Again, 2 miles per hour, but there's an increased grade. The next stage is 4.5. Now we're starting to get into some real exercise. Again, still very slow, but the grade is pretty substantial, 7. And then you keep going up in METs until it gets fairly intense by the very end. So that's for poorly fit individuals. Now let's look at more standard individuals. So this is the standard bulk protocol for normal sedentary subjects. So these are healthy people. They're just, a little bit sedentary. Stage 1, jump right away to 4.33 METs, 3 miles an hour at 2.5 grade. So let's go to a brisk walk. And then you continue to keep the 3 miles an hour, but now you increase the grade till it's really quite substantial. And so this is a little bit more intense than the previous one. And of course, it makes sense. This is for healthy individuals that just happen to be sedentary. Each stage lasts 2 minutes. Now let's look at the Bruce protocol for young active subjects. Here we jump right in stage 1. We go right to 5 METs. So this is a speed of only 1.7, which is very slow, but the grade is 10%. And then you go to the next stage. Each stage lasts 3 minutes, by the way. So you go to stage 2, which is 7 METs, speed of 2.5, increased grade, and so forth. You can see by the end, you're going at 5 miles an hour at an 18% grade. And that's 16 METs. So that's a pretty substantial exercise. So you'd be using 16 times more oxygen than you would at rest. So that's pretty intense. The last protocol is the Astrand and Rodal protocol, and this is for very fit subjects. Stage 1, it starts at a very high level. So each stage actually has 2 parts to it, a vigorous warm-up and then the actual test. And each stage only lasts 2 minutes. So the warm-up is 12.9 METs. And what's happening is it's a speed of 7 miles per hour with a grade of 2.5. And then for the actual test, you'd speed up to 10 miles per hour, again with a grade of 2.5, and that's the equivalent of 18 METs. So that's pretty substantial right away. And then you would increase in various stages, getting all the way up to almost 25 METs, which is really pretty incredible. It's very high. Here are some more take-home messages. When selecting a graded exercise test, the population being tested must be considered. The initial work rate and rate of change of work rate, in other words, how much you change the work rate from one stage to the next, needs to accommodate the capabilities of the population. For measuring VO2 max, the treadmill is probably the most commonly used instrument. It has a number of advantages. The first is that it involves very natural activities such as walking or running. It can also accommodate a wide range of subjects depending on the different level of fitness, from least fit to most fit. It's very flexible. You can increase the work rate by either increasing the speed and or the grade. And it's used for estimating VO2 max. Typically, the most typical method is the one we already talked about. It's usually based on extrapolating the submaximal heart rate to the maximal heart rate and then figuring out either the work rate, or if you have the equipment, you could actually measure the VO2 usage at that maximal estimated maximal heart rate. In these submaximal heart rate experiments, or tests, I should say, the test is terminated at 85% of the age predicted maximal heart rate. There's actually even a possibility of using a single stage test in which the people they exercise for 6 minutes, and then we're able to determine VO2 max. And we'll talk about that test a little bit later. There are some disadvantages. It's difficult to measure something like blood pressure because of the amount of movement the person's doing. There are also potential artifacts for an ECG or electrocardiogram recording, again, because the person's moving their arms and so forth. So for an ECG, a cycle ergometer would be better. Another disadvantage is that people have to be trained to not hold on to the railing. If they hold on to the railing, this will decrease their heart rate, essentially decreases the work rate. And so it would lead to an overestimate of VO2 max. Let's take a look at the use of the bulk protocol for measuring a normal sedentary subject. This person is 45 years old. We can estimate their heart rate maximal value would be 175 beats per minute. 85% of that, which you can arrive at by multiplying 175 by 0.85, would be 149. So this person starts off at a grade of 0%. And with this bulk protocol, the grade is increased in increments of 2.5, but the speed is maintained constant at 3 miles per hour. So basically, the work rate is going up as the grade increases. Now, initially, the heart rate doesn't increase that much, and that's presumably because the stroke volume is increasing, which is helping to increase the cardiac output without that much of an increase in heart rate. Eventually, as we know from what we discussed before, the stroke volume should plateau. And at that point, increase in cardiac output would be primarily due to an increase in heart rate, which you can see here. So heart rate then becomes quite linear. So if we take, eventually the person reaches this target of 85% of the maximal heart rate. And so the exercise is stopped, the test is stopped. Now we could take these last two data points and extrapolate up to this person's theoretical maximal heart rate, which is 175 beats per minute. We can drop down to see what the work rate was. Well, in principle, this person should have been able to keep up working up to 20% grade at 3 miles an hour. And the number of metabolic equivalents is 11.6. So if we want to calculate VO2 max, it's relatively simple once we have the number of METs. 1 MET equals 3.5 milliliters of oxygen per kilogram per minute. So you just multiply 11.6 by 3.5, and you arrive at 40.6 milliliters of oxygen per kilogram per minute. And that's this person's VO2 max. Another way of measuring VO2 max is with a cycle ergometer. It's a little bit different in the sense that compared to the treadmill, the body weight is now supported. This can accommodate subjects with orthopedic limitations. Work rate is determined by resistance on the wheel and pedal rate. Pedal rate is usually maintained constant around 50 to 60 revolutions per minute, And the way it's maintained is by having the person pedal while listening to a metronome, or by providing feedback, such as a digital display of revolutions per minute. And then the work rate is usually changed by an increase in resistance on the wheel. We can estimate VO2 max based on extrapolating a submaximal heart rate during an incremental test, and one of the most popular protocols is called the YMCA protocol. We can use the YMCA protocol to estimate maximal work rate and then calculate VO2 max using the following equation. Now, I believe this is the correct equation. I found this within a different part of this chapter. The one that's actually given on page 359 doesn't appear to work. It seems to be incorrect. This, however, is the correct equation here. The YMCA protocol is quite a nice protocol. It makes use of the observation that the relationship between VO2 and heart rate is linear between 110 beats per minute and 150 beats per minute. And therefore, it only requires a subject to exercise at one more work rate past the one that yields a heart rate greater than or equal to 110 beats per minute. And then from there, we can do a linear extrapolation to the person's maximal heart rate. So each stage is 3 minutes. And for the YMCA protocol, everyone starts off at stage 1, which is 150 kilogram meters. So this is the same thing as a kilopond meter. Okay, so that's so again, kilopond would be a unit of force multiplied by meters. So that's amount of work, and then we're dividing by minutes, so it's a work rate. Okay, so we start off at this 150 kilogram meters per minute. And then what you do is you pay attention to the person's heart rate. So in the last 30 seconds, you'd measure the heart rate. And then if the heart rate is less than 86 beats per minute, you could then go on to stage 2, being a huge jump, which would now be 600 kilogram meters per minute. So it looks like the meters is missing here. It should be kilogram meters per minute. If it's still below that, they would go on to stage 3. So they'd go and go up to a very high level work rate. Now, let's imagine the person isn't quite as fit as that. So if their heart rate is between 86 and 100, then instead of jumping all the way to 600, they're going to go from 150 to 450, and then progressively move up from there. And again, as soon as you have, so the subject must exercise at only one work rate past the one that yields a heart rate that's greater than 110 beats per minute. So let's imagine you get to 110 beats per minute, you'd go to one stage further. Let's imagine that this person right away with stage 1 already has a heart rate that's pretty high. It's greater than 100. They would go on to this easiest pathway. They do 300 kilogram meters per minute, then to 450 kilogram meters per minute, then to 600. And eventually, at some point, we should have the 2 data points that we need. Let's look at a specific example of a person and their analysis using the YMCA protocol. So this is a female, age 30 years old. So their estimated heart rate maximum is 190 beats per minute. If you multiply that by 0.85, it yields 162 beats per minute. So we're going to stop the test when she reaches that level. Her body weight is 60 kilograms. So we only collect 3 data points. First of all, here, if you look at this graph, we have heart rate on the y-axis and we have work rate on the x-axis. And so you can see she's starting off, as everyone does, at a work rate of 150 kilogram meters per minute. So her heart rate at that point is below 110. It looks like it's 105. So she now goes to the next level, which is 300. Here, she does have a heart rate above 110. Okay, so that'll be our first data point. And then she goes to a work rate of 450, and that's our second data point. So at 300, she had a heart rate of 115. At 450 work rate, she had a heart rate of 128. Now we can just draw a straight line using those two data points, and we extrapolate all the way to her estimated maximum heart rate, which is 190 beats per minute. Then we drop down and we see what the work rate is. So her work rate is 1,200 kilopon meters per minute. Okay, and then so that's good. We have now her maximal work rate, and we actually didn't notice that she didn't have to. She really didn't have to work all that hard. We just did three stages. We got 2 data points, and then we're still able to actually figure out her maximal work rate. And then given the work rate, as we'll see in the next slide, we can then calculate her VO2 max. Now that we've found that the estimated maximal work rate of this woman is 1,200 kilopon meters per minute, we still want to calculate her VO2 max. So we're going to need her body weight, which is 60 kilograms. We can then plug these values into this equation here. So I've done that here. I plugged in her maximal work rate and her weight or mass, and we get a VO2 with units of milliliters of oxygen per minute of 2,580. Now, we may want to normalize this by the subject's body weight. So we simply then divide by her body weight, which is 60 kilograms. And now we have VO2 expressed as milliliters of oxygen per minute per kilogram, and it's going to be 43. There's another test, which is quite an interesting one. This is a single stage test. So instead of having 2 or 3 stages, this is a 6-minute test. It was developed by Astrid and Ryming, and it's called a nomogram, or at least this graphical presentation of the test is called a nomogram. And it relies on the idea that the heart rate must be between 125 and 170 beats per minute. So you need that. That's one requirement. And the second thing is you need to measure the work rate. So we could take an example of a man. He's going to have a work rate of 200. So let's look at this nomogram. So we go over here. You go to the male symbol here, work rate of 200. So that's going to be right here. And then we look at his heart rate. His heart rate is 166 beats per minute. So that's up here. And now what we do is actually quite clever, is you draw a line, a dashed line between the 2 points. And then we have another scale here, which has the max VO2. And where this dashed line intersects the scale with the max VO2, that's actually the max VO2. So the line intersects the VO2 max line at 3.6 liters per minute. So that is, in fact, his heart rate. Now, this is assuming that this person has an age of about 25. Now, you have to correct based on age. So let's say the person's actually, let's say the person's 40. Then you would take this value of 3.6 and you'd multiply it by a correction factor, which in this case would be 0.75. And so that would yield a lower VO2 max value. If for some strange reason you didn't know the person's age, there's another way of doing the correction, which is you can use the person's maximal heart rate. So if there for some odd reason you knew the person's maximal heart rate, but not their age, let's say the person's maximal heart rate was 180, then instead of using the age-based correction factor, you could use one based on heart rate. So if the person's maximal heart rate is 180, you could use this correction factor. So for whatever value you found for VO2 max, like say this 3.6, you would then multiply it by 0.83, and that would correct for the person having a slightly lower maximal heart rate. Another really good way to measure a person's VO2 max is using a step test. Step tests have a lot of advantages. They're simple, they're inexpensive. You can vary the protocols by varying the step height and the step rate. And you can estimate VO2 max based on extrapolating the submaximal heart rate, just as we could with the treadmill or with the cycle ergometer. And we can also use the same aspirant and rhyming nomogram that we just used previously. So continuing with the advantages, the energy requirement is proportional to body weight. So as a person increases in weight, they're going to use more energy, which is similar to a treadmill. Work rate can be varied by altering step rate and step height. The rate and this is more not an advantage, but just how you do this. The rate of stepping is established with a metronome. So you typically have up, up, down, down. And you have to make sure the subject steps all the way up and all the way down. Let's look at an example of a 60-year-old female who's going to do the step test. The height of the step is going to be kept constant at 16 centimeters. The rate of stepping will increase by 6 lifts per minute every 2 minutes. And we're going to stop this test once she reaches 85% of her maximal heart rate, which is estimated by age. So let's look at this. So her estimated, based on her age, her estimated maximal heart rate is 160. If we multiply that by 0.85, we get 136 beats per minute. So we're going to start her off with a step rate of 15 steps per minute. Step height is constant. And she has this heart rate, looks like about 112 or something like that. And then she goes up to the next step. She's now increasing to 21 steps per minute, same step height, and now her heart rate is increased. Now she goes to the next step, and now her heart rate has actually reached the 136, so we'll stop the test there, okay? And now what we do is we take the last 2 data points and extrapolate to her maximal heart rate, which is 160 beats per minute. And then we drop down to the x-axis to see what that step rate was. Well, it was 39 steps per minute. So in principle, she only had to do up to 27 steps per minute. But in principle, this suggests that she could have done a lot more. She could have gone all the way to 39 steps per minute. And then we can look at what that is in terms of metabolic equivalent tasks or METs, and it's 7.5. And recall that 1 MET is 3.5 milliliters per minute per kilogram. So we can then take the 7.5 and multiply it by 3.5, and we'll now arrive at a VO2 max. So her VO2 max is 26.25 milliliters per minute per kilogram. So there's a table in this chapter, table 15.1, which gives you a lot of data based on age and sex. And so this subject's actually very fit. The subject is between the 85th and 90th percentile on this table, which is and that's comparing her to women aged from 60 to 69 years of age. Again, in your book, there seems to be a problem. There's an equation on page 360 for step tests that appears to be wrong. I haven't been able to locate the correct equation, but what I presented here in this slide is in fact perfectly correct. It turns out that the same nomogram we used previously for the cycle ergometer test can also be used with a step test. With this, in order to use it, the step test should have a rate of 22.5 lifts per minute, and we should use a step height of 40 centimeters for men and 30 centimeters for women. The results for a 61 kilogram woman are shown. So the first thing we do is we look for the woman's weight. So here it's 61 kilograms. We put in her, at the end of 6 minutes, her beats per minute is 156 beats per minute. And then we draw a line, and then we find the VO2 max. It's 2.4 liters per minute. Let's assume she's 25. We'll go down here. We see the correction factor is 1. Therefore, we know that her VO2 max is actually 2.4 liters per minute. So one idea that may seem a little crazy is that certain epidemiologists have tried to figure out if VO2 max can be estimated without doing any sort of exercise test whatsoever. And the reason they want to do this is because this would allow them to essentially look at do surveys of lots and lots of people and see what sort of risk factors are correlated with VO2 max. So it turns out that it's actually possible. You can estimate VO2 max with a standard error of plus or minus 5 milliliters of oxygen per kilogram per minute, which is actually not terrible, based on a survey in which you asked for the person's age, their gender. You would have to figure out their body fatness. So I suppose maybe that might be a little bit more involved. And you also need to have their self-reported level of physical activity. Given these things, you can then put these things into an equation and then figure out the VO2 max. And it turns out that it's actually very helpful. You could take any one of these individual things and say, well, how is age correlated to, say, cardiac arrest or some sort of health outcome? But if you take these all together and you weight them properly so that you get an estimate of VO2 max, that actually turns out to be very predictive. So people with a higher VO2 max, well, they're healthier and they have a lower incidence of risk of, say, cardiorespiratory problems. So it actually works surprisingly well and can be useful to predict health outcomes in people and things like that. Now, of course, this shouldn't really replace a field test or any of these submaximal graded exercise tests that we've talked about. The big advantage of having someone actually doing a test, and some of these are simple enough that they could actually do it on their own with a little bit of training, is that the submaximal graded exercise tests are very motivational and educational. They tell a person very specifically how they're doing in terms of their cardiorespiratory fitness, and it also can motivate them. They could do some exercising, a month later retry the test and see how they did, and if they show improvement, that's a great thing, and then they're motivated to continue with the exercise, which of course is the goal. Here are the take-home messages. VO2 max can be estimated with the extrapolation procedure using treadmills, cycle ergometers, or a step test. The subject must follow directions carefully, and environmental conditions must be controlled if the estimate of VO2 max is to be reasonable and reproducible.